Hi student, so we're going to look into another topic which is the string matching. So this is different from the what we have learned previously on mostly on graph theory. So what you're going to learn here is about string matching. So basically string matching it well it was born due to the due to the technology where DNA are being used. The DNA has a string of patterns, okay, indicating the double helical structure, okay, that forms the DNA. So, in order to do matching of certain DNA string, so this is where the string matchings are being fully utilized. Other than looking for string matching of a words in a text, I mean for words within a group of text, right? So let's look at the definition of string. So string matching is a searching algorithm which you try to find places where one or several strings, okay, or we call patterns over here, and are formed within a larger string search, okay, or the search text. And for example, we have this. If you see here, we have an example of a string, and we would like to find a pattern of is, okay. So by using, over here might probably using brute force, and you found a place where the matching patterns are found, right? Formally, both the pattern and search text are concatenated of elements of an alphabet, right? So it's a finite set of combination of the alphabets, right? So here nothing more than explaining that it can be usual for human alphabet, for example, the Latin letters, okay, through Z, A through Z, or Greek letters from alpha to the epsilon notation over there. Other application may include binary alphabets, 0, 1, or DNA alphabets. It's a combination of A, C, G, T, and these are the double helix structure. And now, we're going to look into the easiest method, which is the naive method, or or another one where we call it brute force. Okay, so in brute force, okay, you have this nested loop. All right. So this is the first loop will be the index for search text, and the second loop will be the index for pattern. All right. So over here, you're going to see that this is J and this is I. All right. So this is the search text and this is the pattern. As long as I is greater or equal to M, okay, if I or greater or equal to M, and you're going to return back to the next loop. Right. That means you start J and you have to go through this first, okay. Once it's I equal to number of J, and it needs to return back to here and process again in I, okay. The main features of this is easy, but it's actually a slow algorithm, okay. So this is the time taken, okay, and by M. All right, it has no pre-processing phase. Okay, later we're going to look at the KMP method where it has a pre-processing phase where you're going to perform an dynamic programming on it. And the only constant extra space needed, okay, because it shifts just one point to another point, is always shift the window by exactly one position to the right. All right. Comparison can be done in any order, and this is the time taken for comparison. Let's look in one example of this, right? So you have this search text, right? So you put it search text. So this is the length of the search text. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So j equal to 0 until j is equal to or less than 11. Right. So we start with the index 0. Sorry. 12. So j should be less than or equal to n minus m. Right? The numbers of the here. Okay. So you're going to put it 12 minus 11. Alright, so you're going to get when it starts to 0, it is less or equal to 1, right? And once the loop is done, then you increase it 1, right? Now, for I equal to 0, okay, so as long as it's less than the number of pattern that it has here, okay, if it's equal, then it will return back to here. So now let's look how it process. So we start with A, okay. A first try will go on every part here. So I, and it will go to J, right? It's match, so it increase. Sorry, this is J, this is I, right? So this is I. So it will look into here. It match, it match, it match, it match, match, and match. But this is the part that it is mismatch. So on the 7 character, once it's done that, so it needs to go to the next one. Okay, so that means there's a I is equal or greater than the M. Okay, that's the mismatch type part, right? So M is the index of here. Okay, so once it could not find, once it found a mismatch on the 7th character, right? That means I is 7 and it is greater or equal to, okay, here 6, right? Because it's actually greater than equal to 6 because this is the mismatch part. So it stopped there. So you need to return back to J. Okay, so J will increase by 1. Okay, so 0 and 1, so increase by 1, and it will start the next position over here, and this whole string will be shifted to the right side. Okay, so it's always, if you notice that the brute force is always checking the first prefix, okay, until you found a match. So it does not need to go through every element of I, right? As long as it checks the first prefix. If it's not matched, then it will move to another part, right? So here it's not matched. So on the first character, it will increase J. Okay, so this is 0, 1, 2, and I will always start with the first index of the I, right? So A and C is not matched, D and A is not matched, but the next one it's matched. Once it goes that, it will go checking every element of the string. So it's actually a match, a found match. So naive has no preprocessing. Okay, it has the time taken of n times by m. Okay, n is the length of the search text, m is the length of the pattern. Now we're going to look later on the KMP and also Boyer-Moore. All right, so KMP have the m time and end time. All right, why? First, it has the pre-processing, so that will take some time of m, and matching takes some time of n. Boyer-Moore will have m plus, okay, the summation of the a group of numbers, right? For matching, is actually it's just the time taken is mostly on the big O of n, right? So let's go into the next one. This is the KMP, all right? So KMP reduce the processing time by not redoing what has been processed before. That means it has a pre-processing, so it's a dynamic program. Once it has a memory of it, it will not process it. Right? So it has a two component. One is the pre-processing of the pattern string X. Okay, so this is X, and search for the targeted pattern, which is dy. Right? So sorry, this is search tag. Sorry, this is Y. Search tag. This is the pattern, which is X. Okay. So the search tag has 12 and 7 in this example. Okay. So over here, the main idea of KMP is to search the main string that should go in one pass. Right? I mean, you're going to put a main string and you're going to look it in one pass. Okay. So limiting on the return back to the origin. So this is a good strategy since the main tag is normally much longer than the pattern string. For example, if you have a DNA string, so it will take a lot of time. If actually when you don't find a match, and you need to redo and redo and redo. So now, if the search of a pattern on the search tags fail halfway, we should roll back as minimum as possible. Okay, that's the keyword, the minimum as possible, with the help of a memorization table, rather than start at the beginning of the pattern string like the naive method that we have seen earlier. So the main here, okay, so this is go in one pass, right? So you have a search string in one pass. So you're going to look into, you have index of G and I. So again, the same thing. So you're going to check, okay? And you found, let's say you found a pattern search halfway fail, right? So what you need to do is, in the naive method, you just increase J and you start back at the beginning, okay? But for the KMP, once you found a fail, you're going to move step back, okay, to the next one, right? And you'll point to the next one until you reach a match. Actually, you're going to jump into a match element over here, right? And text over here. Once you found the match, then only then you increase the I. So you only backtrack as just enough. Okay, so you don't need to actually backtrack as how the naive method works. So okay, so you know that KMT has two components. All right. So firstly is the search processing. So first you need to find, you need to perform the pre-processing on the pattern, right? So this will take the time of the number of patterns. Okay. All right. So let's look into the first component of this, which is the pre-processing. Okay, over here, this is just an example of having some identify index, right? Where this is the part where you actually to identify a certain repetitive pattern in a string. Okay, so please look into these comments, right? Where you're going to see if A, okay, X at I position, okay, so which is this, if it's not equal to the A and J, all right, so this is, and then these are the condition, right? So these are the perform that you're going to apply, right? So you're going to look later on. Okay, let's look into this simulation. Okay, so you initialize the first string or the first character as 0, right? So you have the pattern X, and you're going to have the pi or LPS, okay, which is this, as the longest proper prefix, right? So this is the number of occurrence of prefix, right? here. So first you're going to start j as 0, and you're going to start with the next string. Okay, so you increase I plus 1. Okay, as long as xi is not equal to xj, since j is equal to 0, right? So j is equal to 0, so the pi should be 0. And then if and then x1, okay, this x1 is not equal to x0, so the next string. So pi 1, okay, which is this, is equal to 0. So you have this, okay, and then you're going to increase I. So you're going to increase I, right? So you move I. Okay, the main reason why it's not moving is because of you don't find any repetitive pattern yet. So J will remain, I will move into one position. And then same thing, we're going to look at it. So X, I and J is not similar. Since J equals to 0, pi is still 0, right? So you don't find any matching or repetitive. So x2 is not equal to x0, so x2 over here is not equal to x0, and the index of the pi is still 0. Okay, so you increase 1, so you increase another 1. Same thing happen, right? So you don't find any repetitive, but once you increase 1 over here, then this is something different that is going to happen. So you have the xi, okay, which is this, the content of a xi with the content of a xj, it's equal, right? And once it equal, so you'd say that j plus 1, okay, that means there's a mesh to increase j. And then at the index x4, right, is equal to, okay, the index is 0, and this I will increase 1 as well. So sorry, it will add 1, right? So 0 plus 1, okay? So previously you have 0, so you plus 1, then you get 1. And then you're going to increase I and increase j. So j is already increased, so you're going to increase I. Okay? Alright, now j has moved and I has moved. Okay? Now, same thing happened. Index number 5 for x and index number 1 for x is actually equal. Okay, b and b. And now j increased to another 1, and then this original index will have 1 plus 1, right? That's why it become 2 over there. Then you increase it to j. Next, you have x over here. So now the content of the index 6 is not equal to index 2, right? Which is in C, x and C. So instead of the j, instead of increased by 1, so j right now is, by using its index, j minus 1. Okay, that means the index of here, we will take this. Okay, so let me see. Okay, this minus 1, okay, equal to 1. So 1 will put it into here where j is minus 1. Okay, so j is going to, actually it's not, it's wrong, right? So x, let me delete that first. Okay, let me erase this. Okay, now the index of p, j minus 1. So I mean j minus 1. So it's actually move here. Okay, j is equal to the content of here, which is 0. Alright, and as long as the I is not and you're going to check it, so here is still not equal, right? So you're going to have pi as 0. Okay, so you're still going to mark that as 0. Now if j is 0, now j containing this, j is 0, and x6, okay, x6, okay, sorry, it will do the comparison first, right? So again, it will need to move backward. Okay, so j minus another 1 over here, alright, which is 1 minus 1 equals 0, so it will have this, and j will have the value of 0. It cannot go further, okay, even though a and x is not equivalent, but it cannot go further, so that's why it say that 6 is not equal to 0. Okay, so this is the last part, and now once you have finished that, then you say that p6, okay, p index 6, right, is going to mark as 0. Okay, now j do not increase because there's no match, only I increase. Okay, so j retain over here, I has increased. Okay, so now x7 is actually equal to x index 0, right? And j plus 1, okay, because it's matched, j plus 1, and p7 will have 0 plus 1, so that's why you have 1 over here, right? And now because of both are matched, so both will increase. Now once you increase, okay, you have another unmatched. Yes, so index number 8 is unmatched with index number 1, right? And you know that j it have to minus 1. Okay, 1 minus 1 becomes 0. Again, a is not matched with c, so it has a 0 over there. Okay, and sorry, 0 over here, and j is equal to 0. x8 is not equal to x0. Okay, so this is the final checking, and p8 will be marked as 0. All right, so this is the pre-processing. This is one example. Let's look another example. Okay, let's have this search text, and we're going to actually look into a pattern of the string. So you're going to initiate first start with j and initiate as 0. Now you go to a. Okay, a, right, index 1 with index 0 is equivalent, so j plus 1 and sorry, I is equal to j plus 1, and the index of 1 will increase by 1, right? So it will increase by 1, so I will be increase. Okay, so this will be increase. Now next you do the same thing, so you found that a is equivalent to each other, then perform the 1 plus 1, okay, because 1 plus 1 you get 2, and you increase both into the next one. All right, so you found the next part where I is not equal to the index in a. All right, so here 3 is not equal to 2. All right, so j will push 1, and we will check it's not equal, and it will check until the end. All right, so until the end 3 is not equal to 0, so this is going to mark as 0. Only I will increase. Okay, so I will increase. Okay, j will return back to here. So now the next one, the index 4 and 0 is matched. So remember here is you set to 0, so 0 plus 1, so you get 1, and both will increase 1 again. Next iteration, it has the same match, again increase another 1. Okay, and this will increase 1 plus 1 just now 2, so this 2 plus 1 become 3, right? So you'll be repeating the same thing. Okay. Now this is interesting. Now J is not matched with I. So index 3 is not matched with 7. Okay. And then J will go one step further. Okay. Now here it's matched. Right. So it get this value. Alright. Hold on. So it goes one step back. It found a match. Right. For I, will increase by 1. Okay. And then at first 7 and 3 is not matched, but the next position index where J is equal to 2. So here this string are matched, 7 and 2 are matched. Alright, so originally here is 3. So instead of 3 plus 2, you're going to get this value 2 plus 1. So it becomes 3, right? Okay, now both will increase back. So J will increase back to its original position as previously. Okay, from 2 to 3. So now it returned back here. Okay, so the same thing happened. It will return back over here 2 plus 1. Then that's why you get 3 over here. Then both will increase back. Okay, and this will increase back. And when it reach the index 9 and then index 3, okay, index 9 is the final one. So 9 is equal to 3. Sorry, index 9 and index 3 is equal. See? Alright, so it increased here. 3 plus 1. Okay, become 4. So now you have this pattern processing. So this is the number of occurrence of the pattern of a certain search string, right? So first, with pre-processing done, the pattern matching process is relatively simple. So once you have done that, so you're going to do the search pattern, right? So in main search, it runs and time of it, okay? And here you're going to look at the while loop. Okay, this is the J and this is the I, and you're going to perform the matching. Okay, okay, if it's equal, I is greater than or equal to M. Okay, M is the number of here, right? Then it will return match. Otherwise, it will return as mismatch. So the total type of KMP is actually you have the pre-processing and the pattern matching. So now let's look into this example. All right. Over here we have this string. Okay, which are calculating the number of repetitive value. Okay. So you can actually put it something like this. So where you have, hold on, right? So where you're going to have indicating, okay, these are non-repeated. Over here is the repeated value. So this pre-processing can be done for rechecking with the pattern searching. All right, so that's what we have. We did on this part. Okay, so the P will be placed over here. So now let's look into this simulation. Let's say you have a pattern searching right now. So this is your search text. So this is your pattern. So you're going to find a mesh with this, right? Let's start everything with 0. Okay, so I is equal to 0. So this is the index, not the P, but we are looking into the index. So I and also J, right? So Y over here, J is equal to I, okay? That means if it's matched, the content is matched, then you increase I and J, right? And this is true later on because it's match. Okay, so after about 5 iteration later, okay, you're going to jump into here. Okay, so this is the final one, b, okay, and you're going to increase I, and you're going to increase j, right? So this is where I and j contain one. Okay, if you see the checking here, it says that, okay, these are the repetitive pattern, but over here it written back to 0. Okay, that means in this area, uh, there's a mismatch. Okay, and it's not being it's not a match pattern, right? So hold on, what it does is, in the next step, let me, in the next step, it needs to return, okay, here is already 0, so it needs to return 2 step. Okay, so you look into I and you find out what's the number of steps that it needs to return back. Okay, so you return I, okay, but j is you're going to increase back, okay, 1 and 1. Okay, so basically it's supposed to have 6 here. I think I missed that. I jump 2 steps there, right? So what it does is, in 6 it will move 1 and this will increase 1. Okay, so it will do a comparison whether a is equal to c. This will remove 1, this will keep on, j will keep on continuing increasing. The one that always backtrack is the I. Alright, so I found a match here. Okay, so d is actually equal to d here, and you're going to increase back I and also j. Okay, so now a is equal to here, right? So you're going to increase b is equal to here, and you're going to increase d is equal to here. Okay, what it means here is that the match string is up to here. Okay, and it will stop this area. Okay, but if it go further, the one that is going to match will be DABD, right? So DABD will be match. Okay, but at this moment the only match pattern is ABC up to DA and B. So over here there's a failing, right? So it's supposed to terminate. So let's look into the second example. Okay, again you have this match, and you're going to increase 1 by 1. Okay, but over here there's an unmatch. Okay, index 2 in Y, J, and the one index I here. So what it does is, it needs to move back 1 and check it back with this. Okay, this is not match, and you move back another 1. Okay, until A is until A over here is mesh with that, right? So the I will return back to 0. So okay, because of this, right? And it will keep on checking whether it's found a matching or not, right? So over here, because of over here, J will keep on increasing, right? So J will start over here, and I will return back to the index 0. And then this is match. A and A here and A here, it's match, alright? And then increase I and J. Okay. And then here, again, it's match. Then you can increase back. And here, it's still match. And then you increase. And again, here is match. You're going to increase. Okay, now you found there's an unmatched there, right? So you're going to, I is going to return back one step behind. Okay. And hold on, one step back, and B is still not matched with this, and you're going to perform another step behind. So A is actually matched with this. Okay. A is actually matched with this, and now, okay, and now the string over here, okay, you already found A, B, and this one now you're going to increase to 1, okay, and you're going to check whether this is equivalent or not. Okay, then this is a match, and this is match, and this is match. Okay, so this confirm that AB having this pattern and having this pattern. Okay, 0 0 1 2 and 1 2, right? So here is the match parts, okay, AB, and also match part AB, right? But you don't go for you don't match over here because the I is only reach up to here. Okay, so that's the KMP. Now we're going to look into the Boyer-Moore algorithm. All right. So Boyer-Moore is actually try to solve the problem of the brute force search. Okay, and both KMP and Boyer-Moore is actually try to reduce the numbers of m times n here. All right. So it works the fastest when the alphabet is moderately sized and the pattern is relatively long. Okay, if you have a long pattern and you have a moderate alphabet, so this is will be a quite powerful algorithm for search method. So again, it has two properties, right? Or here, two approach. One is to find the bad character approach. Another one is to find a good suffix approach. So both approach can also be used independently to search a pattern in text, right? But here we will discuss about bad match approach. Okay, so you're going to create a bad match table later on. So Boyer-Moore algorithm does pre-processing. So again, here is it implement dynamic programming. So why pre-processing in Boyer-Moore? Compared to KMP, here you're going to shift the pattern by more than one character, right? So there's a shift of a string actually. So the character of the tag which doesn't match with the current character of the pattern is called the bad character. Upon mismatch, we shift the pattern until the mismatch became a match, right? So you push the whole string, until you find a match. and the pattern P move past the mismatch character, right? So if the mismatch occur and the mismatch character not available in the bad match table, then we shift the whole pattern accordingly. So you're going to look later on how we're going to perform that. Okay, I think I'm not going to look into this. Okay, good survey approach. What we're going to use is the bad match approach for searching, right? So these are the steps. First, you need to construct the bad symbol shift table. You're going to align the pattern against the beginning of the text, and you're going to repeat the following step until either a matching substring is found or the pattern reaches beyond the last character of the text. So you're going to use a formula, okay, to construct the bad match table, where the length of the pattern minus with the index, okay, and minus by 1. For example, here, now we're going to do the pre-processing part, which is a constructing of the bad match table. Alright, so let's see this example. So you have a pattern of here, team must. So with the length of 8, 1, 2, 3, 4, 5, 6, 7, 8, right? Remember that. And you're going to index it, okay, starting from 0 until 7, right? So now we have this table. So we arrange, arrange the just a single text. Even though if there's a duplicate text over there, you just use one single text. So here you have TEAMS and star indicating other than characters that is not found in this string, right? In this pattern. So here, let's start with here, right? So in order to get this value, so you know that, so you get maximum of the 1 or the length of string, okay, which is 8 minus index, which is 0. Now you start with the index 0 minus 1, right? So 8 minus 0 minus 1, you get 1. So between this 1 and you get 7. Between 1 and 7, 7 is the highest. So you put it into this table. All right. In the next iteration, now your index is 1. Okay. Again, your length is same. Your index is 1, and you minus 1. So you get 6. So you put it there. And then you shift to another character of the string. So the index is 2. So you get 5. Okay. And this one index is 3. You get 4. Here you get 4, index of 4, you get 3. And here, the index is 5, you get 2, right? Alright, sorry, this is wrong. Sorry, this is, okay, before is 5, now you get 2. So you're going to update this. You replace the previous number, alright? And S is 1, and T, now this is interesting, T is 7, so 8 minus 7 is 1, 1 minus 1 is 0. And which one is the highest one? So it's 1. So this one will go to replace T. And then it says that any other numbers is equal to the length. So here we're going to put 8. All right. So this is the shift table algorithm. All right. So this is the pseudocode that you can look into. Right. So here is you get the length of the pattern. Right. So this is the part that you get the length of the pattern. And what you're going to do is you're going to create a shift. Okay, so you have a string that you're going to push. Okay, so the pattern is going to be put into a array as a string, right? So you're going to push the whole character into string. And in the loop, all right, so this is actually the same, right? In the loop, so you're going to go index by index, right? From 1 to 0, okay, to the each of the string letter, okay. You're going to perform. You're going to look into this. So this is the part that you have this length. Length of pattern minus index minus 1. Alright. So you're going to put the whole shift into there, right? So this is the shift that you're going to decide whether the this is shift bij, sorry. So you're going to push everything into the whole string into the algorithm. So this pseudocode is only up to this, right? Up to getting the character pushed into the string, and you get the length of string. So it's actually not looking into the max part. So basically you have to have because this is a procedure of creating the shift, right? So you're going to have another procedure where you're going to perform looking into what's the maximum number of the shift. Okay, so this is create shift, and you're going to have a look into whether is it a mismatch or a match within the table, right? So here, let's look into this example. So we performed this earlier. Okay, this is the same table. Okay, so you have 8 over here. Now let's do a searching. Right, let's say you have a text and you're going to find a pattern match, right? So this is the word that you want to look into. Okay, so in the rule it says that you're going to look into the prefix of p, okay, which matches with the suffix of t, right? So that means okay, so you're going to look into the prefix of t into the suffix of the text here, right? So t and t it's found in the bad match table. Okay. So you're going to shift 1. Okay, actually not move 8 space, actually move 1 space to the right. All right, so you move 1 space, and then now this is you found there's a mismatch there, so you're going to look into your table. So O is not there, so O is categorized as others. Okay, so you're going to shift 8 steps, okay, 8 space. So you're going to shift 8 space. All right, so 1 2 3 4 5 6 7 8. All right, actually this is wrong. Move 1 space. Okay, this one should start from here. All right, okay, so assuming that here is T and here is S, right? So when you look in the lookup table, so you see that S move 1 space, so you're going to move 1 space. Okay, not 3 space. All right, so you move actually just now 8 space, and you're going to the new one is you're going to move 1 space. All right, so you move 1 space, then you found the match, right? Yeah, so T is match, S is matching, E is matching, M is matching, and so on, right? Now let's look another example. So we construct the bad match table. How do I get that? So remember this formula: length of string minus index minus minus 1, and you get the maximum value of it, right? Between 1 and the operation that you have done. So over here I got 3 2 1. Okay, how do I get 1 here? Because of 4 minus 3 is 1, 1 minus 1 is 0, so it has 1. Okay, so length of 4 is going to be the other numbers. So let's try look into this. Okay, so we align it and we look at the prefix and suffix. So C and M is not matched, and C is actually not in the bad match table, so you're going to move 4 move 1, 2, 3, 4, right? So you're going to move here. Okay, so T and M, okay, it's not match. You're going to look into this table. You found T. Okay, now move T to 3. Okay, 1, 2, 3. Okay, so you align it, and you're going to find in the lookup table, right? So this one say that 2, so you need to move 1 and 2. Okay, so once you've done that, then you see, oh, there's a match here, there's a match here, there's a match here, and there's a match here. So you're going to stop this this iteration. So the Boyer-Moore algorithm has the most important is to create the shift table, right? The mismatch shift table, and you need to push, okay, the string into the shift table, right? And you're going to look into the table on the number of skips, okay, that it needs to move, okay. And if the number of skip is equal, this here over here, if the number of skips is equal to the length of the pattern, then you're going to break the iteration. Okay, so the pre-processing phase is, okay, for the first time on the pre-processing. So you're going to have the pre-processing is going to have this bad match table. Okay, so this is the summation of the time and space complexity, where it has this bad search table. And it was proved that this algorithm has this processing time comparison with P is not in T. However, this algorithm has M times N comparison when P is in T. Okay, that means if the pattern is not in the text, okay, so the time taken is here. Okay, it keeps on skipping, but once it found a match, right, and it needs to look back in for one character to another character. So this will take about an M. The process that skipping is actually taking 0M. Okay, I think that's all about this algorithm. So I'm going to post another topic on the NP completeness. Since this Thursday is public holiday, so I'll post video, the last video by tomorrow, right? And we'll also discuss in the video regarding your test 2, your assignments, and what will you expect for your final exam. Okay, thank you.